Hi students, now we are going to explain what is gravitational potential energy of a system of two masses. Now we have already studied, if you consider a source mass m1, it will be surrounded by a gravitational field. Inside the gravitational field of the source mass, let us assume a test mass m2 is entering inside. For this, I have to do some work. So the second mass is assumed always to be brought from infinity somewhere where there is no gravitational field of the first mass. And from infinity, the second mass is brought and placed at the point B, which is at a distance r from the source mass. So imagine one source mass m1 and it is surrounded by the gravitational field. From a point outside the gravitational field of the source, I will bring some other mass m2 and keep it at some reasonable distance. For this, work has to be done to bring the mass m2 and place at a distance r. This work done in moving the test mass m2 from infinity up to this point, or from the point up to infinity also we can define. It is our choice only. But as a convention, let us imagine that the work is done in moving the second mass from infinity up to this point first, and let us discuss what will happen next if it is moved up to infinity. So the gravitational potential energy of a system consisting of two masses is defined as what? The work done in moving the mass, second mass, from infinity up to the point B, which is at a distance r from the source mass. So this work done is only stored as potential energy of a system. Here we have to understand this is the potential energy of the system. System means what? It is a combination of both the masses m1 and m2. Suppose if m1 and m2 are almost equal or comparable, slight differences there, almost equal, then we use the term, it is gravitational potential energy of the system, two particle system. Suppose if you take m1 is extremely larger than m2, or m2 is negligibly small in comparison with m1. For example, m1 is the mass of the earth and m2 is the mass of a falling apple. Then we use the term gravitational potential energy of the test mass. Understand? If m1 and m2 are comparable or nearly equal, then U is called the gravitational potential energy of the system. Suppose if m1 is extremely large and m2 is very small, then it is U is called by what name? Gravitational potential energy of the test mass. Okay, both you have to remember. Now we want to get an expression for this epsilon. Epsilon, it is a scalar quantity because it is expressed in terms of the work done. It is a scalar quantity. Okay, now let us understand the diagram. So m1 is the source mass which is placed at a point A. m2 is brought from infinity and placed at a point B. So that the center to center distance between m1 and m2 is r. Initially it is r. Understand? So there will be a force of attraction between the two masses, and it is given by the expression what? Universal law of gravitation, F is equal to minus g into m1 m2 by r square. That you keep it in mind. Okay. So in this direction, gravitational force Fg is acting. So what is F gravitation? Fg is equal to minus of capital G into m1 into m2 by r square into r cap. So the minus sign is because r cap and this Fg both are oppositely directed. Understand? Now in such a situation, now let us imagine if suppose this mass m2 is moved towards C on the right side. I am going to move this mass m2 on the right side through a very infinitesimally small displacement dr from B to C. So I am pushing it. Okay. So am I applying a force opposite to that of the gravitational force or not? So I have to apply what external force. So in this direction, this is a F external. Understand? So F external is equal to positive of G m1 m2 by r square into r cap. This minus sign vanishes. This is because this external force is acting from left to right. Okay. Now for a very small, infinitesimally small displacement, I am applying a force nearly equal to Fg itself. So the magnitude of Fg is equal to the magnitude of the external force, and that is equal to F. So this is equal to what? G into m1 m2 by r square. Magnitude. So r cap doesn't appear. The same if you want to express then F. Okay, this can be written as G m1 m2 by r square into r cap in general. So this is our equation 1. Now there are two ways. One is what happens when I move this mass m2 from a point B to a point D. So from a distance r to a distance r dash. If I want to move this mass m2 from point B to D, means I have to move from a distance r to a distance r dash. Understand? So this is the external force has to be applied. Suppose if you want to move the mass m2 from the point D to the point B, that is from r dash to r, if you want to move the mass m2, means the external force is not required. Why? Because already there is a force acting on this mass m2, that is gravitational force, which will bring the mass from D to B by itself. So these 2 points I am again repeating. If you want to move this mass m2 from B to D, means work must be done on the system. Or if you want to move this mass m2 from D towards B, means the work is done by the system. The work is done by the gravitational force. Is it not that? So in one case, if you exert external force and do work, means then the work done is positive. Why? Because when the mass is moved from B to D, you are moving from lower potential to a higher potential. So work is done on the system, and hence it is positive. Suppose if you want to move this mass m2 from D to B, then it is moving from a higher potential to the lower potential, means work is done by the system. Is it not? Potential energy decreases. So the work done is negative. These are all we have studied in the earlier chapters, work, energy and power. We are going to apply them now. Okay, now what is the general expression for the force we are going to substitute is G into m1 m2 by r square into r cap. Whether you move from r to r dash or r dash to r, the general expression for the force required to be exerted on m2 is given by equation 1. Okay, now a small work done for a displacement dr, for a small displacement dr, okay, is given by dw. So first, through a small, infinitesimally small displacement dr, I am pushing the mass m2. Okay. So for that, the work done is also very small, is it not? So this is F dot product with the dr. Okay. So this is equal to G into m1 m2 by r square into r cap dot dr vector. So dr vector, this dr vector is also equal to length dr into r cap, length dr multiplied by the unit vector r cap. So now this dw is equal to G m1 m2 G into m1 m2 by r square into dr into r cap dot r cap. R dot r, that is equal to what? Self dot product is equal to 1. Okay. So now dw is equal to what? G m1 m2 by r square into dr. So this is the required equation number 2. Here there is no r cap because work done is a scalar. Is it not? Work done is a scalar. So dw means what? It is the infinitesimally small work. For what purpose? To push the mass m2 from the point B to the point C through a small displacement dr. That is equation 2. Like this, what we are going to do? Here you should be very much alert, my dear students. Here what we are going to do? There are two possibilities. Like this, I can move this mass from B up to D. That is from initial distance R to a final distance R dash. Understand? So in this case, we are pushing towards the right from lower potential to the higher potential. So the lower limit is R and the upper limit is R dash. Suppose if you take this work done from D to B, then the lower limit is R dash and the upper limit will be R. Suppose if you push B to D, means work must be done on the system and work done is positive. If it is moved from D to B, means the work is done by the system by spending its own energy and hence the work done is negative. So let us see one possibility at a time. So total work done, the total work done in moving from infinity to the distance r, that is from r dash to r, okay, that is equal to W. W is equal to integral of dw. So this only I told you there are two possibilities. So this may be equal to what? Suppose r to r dash I will take. There is one possibility. And here r to r dash, when I do r to r dash means this is work is done on the system. So and here work is done on the system and the work done will be positive. Suppose if you take work done is equal to integral of dw from r dash to r. From r dash to r means work is done by the system and this will be equal to what? Negative. So let us take the second choice, okay. So the total work done is equal to integral of dw. This is equal to, that is limits r dash to r. And this is integral of g into m1 m2 by r square into dr. Limits r dash to r. So I am moving towards the left side, that is from D towards B, from initial distance r dash to a final distance r. This work is done by the system. Okay, now work done is equal to, constants can be taken out. So G into m1 into m2 is taken out. Integral limits r dash to r 1 by r square. So this is 1 by r square into dr. So this is equal to G into m1 m2 into, now this is r power minus 2, is it not? R power minus 2. So I will write this is also equal to r power minus 2 into dr. And the integral value, we use the integral, that is the integral of x power n dx. Its value is what? X power n plus 1 divided by n plus 1. This we have been using for all the derivations. This is not integral of x power n. Here in place of n there is minus 2. So r in place of x there is r. So the result value of this integral will be what? R power minus 2 plus 1 divided by minus 2 plus 1, and that is equal to minus 1 by r. So G into m1 m2, the value of this integral is minus 1 by r from r dash to r. This negative sign I can take outside also first itself. So this is equal to minus of G into M1 M2, okay, into 1 by R. 1 by R, lower limit is R dash, upper limit is R. So this is equal to minus G M1 M2 into 1 by R minus 1 by R dash. So this is now equal to minus G M1 M2 by R minus of G1 M2 M1 M2 divided by R dash. So this term, the first term is the potential energy of the mass at a distance R minus the potential energy of the mass at a distance R dash. Okay. Now this is a lower potential, is it not? Lower potential minus higher potential. So this is negative. This work done is negative. So suppose if R dash is equal to, okay, if R dash is taken to be infinity, so from infinity to the distance R, you are bringing the mass M2. So the second term 1 by infinity will become 0, is it not? So the second term U of R dash will be equal to 0. Therefore now U of R is equal to minus of G M1 M2 divided by R. So this is the final equation. This is the final equation number 3. So what do you understand by U of R now? U of R is the gravitational potential energy of the system of two masses M1 and M2 separated by distance R. Why we have got a negative? Because we have moved the mass from D towards B. Work is done by the system. System is bringing the mass from a higher potential to a lower potential by spending its own energy. So here energy is lost. So work done will be negative. That is why we are getting a negative term. I have already told you, if M1 and M2 are comparatively equal, almost same means, then we will have to use the term gravitational potential energy of the system. If M2 is infinitesimally small and M2 is extremely large means, then the same is also called as what? Gravitational potential energy of the mass M2 at a distance R. Okay. So there are some special cases. The same integration also can be done in several ways. If you look at the competitive exam books or CBSE or any syllabus books, the same type of derivation will not be there, but the final equation will be the same. Understand? Now I will tell you, we started with the work done W is equal to integral of dW from the limits R dash to R. Is it not? What will be the derivation if you take the limits from R to R dash? When you take R to R dash means you will land up with U R dash minus UR. Understand? So the work done will be positive. But in both the cases, the potential energy will be negative only. Understand? So one more way of deriving is that directly you can take the limits from infinity to R or R to infinity. That is our choice only. Understand? So what do you understand by gravitational potential energy of the system? It is the work done in assembling the two masses at a reasonable distance. Or it is the work done in moving the test mass M2 from infinity and keeping it at a distance R to form the system. It is a scalar quantity. I hope you must have understood well. Fine.